So annoyingly, I couldn't find a video that explains a simple nucleon excitation, de-excitation, other than they said it. But to be clear, is usually explained for the nucleus before we get to higher levels of quantum, is that it's generally just a ball of the nucleons, of the protons and neutrons, and then it's enveloped by a cloud of electrons that are all in these orbital shells that are weird probability spaces and defined by its wave function. But there's like a ball of the nucleus in the center. But what was really going on is that all of the nucleons, the protons and neutrons, stack up in another set of different cloud shell orbitals. They take on the exact same quantum states as the electron shells, but they do it to a different shape because they have much different masses and the force has different parameters to it. But just like an electron can be excited to a higher electron orbital with a photon, and the electron drops back down from the excited orbital, it emits a photon. Any one of the nucleons in the center, in the nucleus, in their orbital shell model, they can also be excited to a higher energy state while still being in that nucleus. This is what's known as a nuclear isomer. If they're stable, where there's like a nucleus, a specific type of nucleus that you can excite one of its nucleons to a higher state, and it makes that nucleus stable, versus it might not be stable without that excited. So it's kind of like make it an unstable nucleus, but then lock it as stable by exciting one of its nucleons to make it a stable set, even though it wouldn't be a stable number of regular isotope. To kind of give a subtle analogy here, take a look at me pointing. If you watch this, what happens here, the move I do, it kind of gets the whole like orbital motion gets unstable, and it's almost as if like you would have to like shoot it with a photon right at that point where it becomes unstable, and it like locks the poi into a new orbital stable that is stable, that the rest of the motions can stay stable with it without, smacking me in the face and then I drop everything, This is important is because those nucleon excitations, the energy drop, equivalently in a electron orbital shell, the energy drop, it's pretty large, but it's not like crazy. But the excitation drop, or the energy for the nucleon excitation drop, is extremely massive, like crazy massive, that the like energy to weight ratio is that you can like store in a nucleus. To be clear, it's not just unstable isotopes that are locked in as stable isotopes as an isomer with an excited nucleon. It can be regular stable isotopes that just have one of the regular nucleons excited, but that energy drop is huge. It's like even relative to what we know of nuclear fission and nuclear fusion energy releases. This can excite one of the nucleons in depending on what isotope or material or specific one that's being used. The decay half-life of it can either be really long or really short, so you can store energy in these isomers, or these excited nucleons, but you would need it into an isomer that's a stable isomer.